Hey guys, I have your notes pulled up for section 5-6 day 1. This is day 1 of 3 days of related rates. You're going to have notes for all 3 days. They are going to get progressively more difficult as we go along. So this section is very different, kind of weird. The concept is not that difficult, it's just weird, okay? And something that I really need you to wrap your brain around and completely understand before you tackle the types of problems that we're getting ready to do. So, to get you started, I've thrown an equation up on the board. Q is equal to 2x plus 4y squared. I'm going to have you find the derivative of Q with respect to x. So I'm declaring x as my variable. I think you all can do that. I think you all can do that without much help from me. You're like, oh, well, if x is the variable, y must be some messy function. I'm going to have to chain rule it when I get to it. And then you could apply that thinking to the next derivative that I ask you to do. Okay, now start over. Do the derivative of q with respect to y. Some of you are smart enough to take that concept one step further and say, oh, well, if she wants y to be my variable, I can do that. Then x would represent some messy function in terms of y. So when I'm going through doing my derivatives, my derivative on the y term is going to be easy. My derivative on the x term is when I'm going to have to back it up with the chain rule because x is messy. So many of you are able to work your way through the first two derivatives. Now the third derivative is something totally weird. Now I want you to do the derivative on q with respect to t. And you're like, wait, there's no t up there. You're right, t's our variable. So, to help this make sense to you, let me start off by doing a quick review on implicit differentiation. So this is what you're kind of used to on derivatives. If I say, find the derivative of y with respect to x, you're like, oh, I can do that. X is my variable. Look at me go. I'm going to do a derivative. Here's the thing. X is your variable. Y is a function that depends on x. So as x changes, as somebody stands over here and counts and says, okay, when x is 1, what's y? When x is 2, what's y? When x is 3, what's y? And so on. Get it? Y changes depending on what x is. As we count our x's, my y values change accordingly. Okay, so y represents some messy function. Now, when you get over here to an equation where your y is like buried, and you're thinking, oh shoot, this equation is not set up like that equation, doggone it, I can't get it set up like that equation, I'm going to have to use implicit differentiation. So here I go. When I take the derivative on this term, it's easy. When I take the derivative on this term, well, doggone it, I'm going to have to back it up with the chain rule. So once I'm done with my little derivative, I'm going to have to go times dy dx. Remember doing that? Okay, now, in Calc 2, we spend some time on this concept called parametric equations. Don't worry about the name, but here's what it is. Suppose you have a point on a graph, and your point is moving. Your point is moving so that your x-coordinate is changing and your y-coordinate is changing. And somebody has a stopwatch, and they're saying, okay, this is how x is changing. It's based on time. At 1 second, when t is 1, you can figure out your x value. When t is 1, you can figure out your y value. 2 seconds, plug in 2. Figure out your x value, figure out your y value. At 3 seconds, plug in 3. All right? So what's happening here is x is changing based on time. Y is changing based on time. What's our variable? T. What are x and y? Messy functions in terms of t. Just like I would call y a messy function in terms of x, I I would call it the same thing over here. Y is a messy function in terms of x. Now, all of a sudden, I'm introducing a new variable called time. Now, all of a sudden, x is not a variable. X is a function. It's a messy function. So if you're going to do a derivative, and there's an x in there, and there's a y in there, and I say, do a derivative, but hey, guess what? T is your variable. Now, all of a sudden, you've got to treat x as a messy and y as a messy in terms of t. Okay? So, taking that concept, let me go ahead. That's how we're going to approach this green problem. Let's do the derivative of q, and hey, now t is my variable all of a sudden. So let's just go through these step by step. The derivative of q with respect to x, this is an easy one. All right, we're going to treat x as our variable because it says to, which means y is a messy function. So here I go. The derivative on the first term is easy. The derivative on the second term, do the power rule like normal, and then back it up with the chain rule. The derivative of y with respect to x, right? I've stated here that x is my variable, and I've stated here that x is my variable. It matches the whole way through. Next one, let's do the derivative of q with respect to y. Now, I'm declaring y as my variable. What's x? X must be some messy function. So here I go. When I do the derivative on the first term, x is messy. So I'm going to do my derivative like normal. The derivative of 2x is just 2. Back it up with the chain rule. The derivative of x with respect to y. That's weird. But we declared y as our variable, so this is how it's got to be done. Plus, now, since y is our variable, the derivative on the second term is easy. It's just 8y. Now, last one. T is our variable, which here's what that means. T is my variable, so x is some messy function with a t in it. Y is some messy function with a t in it. They're both messy. Every time you encounter them while you're doing a derivative, you're going to have to back each of them up with your chain rule. So the derivative of q with respect to t is first term like normal at first times dx dt. Right? So the 2 is the coefficient, that's my derivative, times the derivative of this function, and t is my variable, and that's how you write it, dx dt. Plus, next term, remember y is messy, so it starts off like normal, 8y, and then the derivative of my y function with respect to t. Okay? Also, keep in mind, as we're getting ready to work our way through, derivatives. Word association. Ready? Derivatives. What else does it mean? It means slope of the tangent. It means instantaneous rate of change. So we're going to focus a lot on rates of change in this section. So this is talking about the rate of change of q with respect to x. The rate of change of q with respect to y. All these derivatives are how q is changing. What is q's rate of change? So keep that in mind. This little paragraph right here kind of backs up what I just said about Calc 2. So let me read it. Let me go through here. Blah, blah, blah. Okay, check this out. X and y are differentiable functions of t. Here's what that means. X and y are functions with a t in them, and we are able to do derivatives on them. So you don't have to worry about if I do a derivative, is it ever going to blow up? We can do derivatives on x and y. So what that means is x is its own little equation, its own little messy equation with a t in it. Y is its own little messy equation with a t in it. This represents, what did it say? This represents, so you got a point moving around on a coordinate plane. This is the distance from the point to the origin. Right? You can distance formula. It's also Pythagorean theorem, especially when it's at the origin. It's totally easy. This represents that distance. If you do a derivative on d with respect to t, remember t's are variable. X is messy, y is messy. When you do a derivative on this, you're going to power rule it like normal. So you're going to bring the 1/2 to the front, same. Lower it, chain rule it. So now we're focusing on the derivative of the messy. So I'm going to do 2x, chain rule the x, 2x dx dt, plus power rule it, 2y, chain rule it, dy dt. All right, we're going to get it started pretty easy. Some pretty easy problems. So here's how it starts. The radius of a sphere is a differentiable function of t. Here's what that means. R is some messy function with a t in it. That's all it means. And we've got V, capital V, is the volume of a sphere. Find an equation that relates the derivative of v with respect to t and the derivative of r with respect to t. Well, before we find an equation of a derivative, we need the original equation. So I'm going to start with an equation of volume of a sphere. I would hope that you know that. If you don't, you're going to know it after the next 30 seconds. Memorize it, because you're going to need it over and over and over again. So, part A, here I go. The volume of a sphere is 4/3 pi r cubed. Memorize that. You're going to need it throughout this whole section. So that's the volume equation. This is saying, hey, let's do a derivative on that, and t is my variable, which you knew t was the variable because it said that t was a variable up here. So we're going to do the derivative on this equation, and hey, when you get to the r, remember r is messy and it has a t in it, so we're going to have to back it up with the chain rule. Here I go. I've got the derivative of v with respect to t. This is how we're writing our derivatives this whole section. We're not doing v prime. We're not doing r prime. We're going to do dv dt. There's a reason for that. Here I go. I'm going to power rule it. When I bring my 3 down, that becomes 4 pi r, lower it, times, chain rule it, dr dt. Remember how r was a messy function in terms of t? So when we get to it, we have to back it up with the chain rule. T's our variable, this matches, t's our variable. This second line here, this is the equation that relates dv dt and dr dt. All right, part B. Starts out by saying r and h are both messy with a t. R and h, they're able to, you can take the derivative of them, and they're messy functions based on time. So this is messy with a t, this is messy with a t. Let V represent the volume of a cone. V is the volume of a cone. We need an equation that has a dv dt in it a dr dt in it, and a dh dt in it. We need all three of those. We can't get that until we have an original volume equation. So volume of a cone, for volume of a cone, you're going to start with the base that's a circle. So you're going to go pi r squared. You're going to take that circle. You're going to multiply it by the height, because that's how we do volume. So I'm going to do pi r squared times the height. However, cones taper. And so the amount that it tapers is it tapers to 1/3. So 1/3 pi r squared h. It's the original volume equation for a cone. Now, you ready? Let's do a derivative on it. We're going to do the derivative of volume, and we're going to declare that time is our variable. So we're going to do dv dt equals, now, be careful. Be careful. You're going to have to product rule. R is its own messy function. H is its own messy function. You're going to have to product rule. So I would say 1/3 pi r squared, that's all number 1 in my function, and then h is my number 2. So as I do power rule, 1d2 plus 2d1, that's what I'm going to do. Here I go. I'm going to scoot down here because I'm going to need more room. dv dt equals. All right. Power rule, no, 1. Sorry, copy it. 1 d2. What's the derivative of 1h? H is messy. It's 1 dh dt. So 1d2 plus 2h d1. So 1/3 pi r squared, I'm going to power rule it like normal. Don't forget to chain rule it at the end. 2d1. So I got 1, no, I don't. Power rule it 2/3 pi r to the first times dr dt. There's not much we can do to this. They're not like terms, so we can't combine them. I'm just going to leave it like that. And it said find an equation that relates them. I did. Here's an equation. It's got a dv dt in it, it's got a dh dt in it, and it's got a dr dt in it. Remember what this represents. This represents how the volume of the cone is changing over time. So if you had a cone shape, tell you what, if you've seen those little water stands with the cone-shaped cups where you pull a cup out and it's an upside-down cone and you're filling it with water, this would be how the volume of your water in a cone cup. How does the volume of the water change each second that you're filling it up? Okay, last one. These go together. Part A. A is the area of a circle where you are. Okay. A is the area of a circle. What's going to be happening here is we're going to picture a circle expanding uniformly. We're going to picture a circle expanding like an oil spill. And it says, find the derivative of A in terms of dr dt. So I'm just gonna do a derivative. So what this is saying is t is my variable, r is messy. So the derivative of a with respect to t is power rule it, chain rule it. Now for part B. Keep in mind, every time you write the derivative of something, it means the rate of change. This fraction represents the rate of change of the area of the circle with respect to time. This fraction means the rate of change of the radius of the circle with respect to time. The rate of change of the radius of the cone, the rate of change of the height of the cone, the rate of change of the volume of the cone. Each of those fractions represent a rate. So, okay, here's where we actually get started on related rates problems. We've got a word problem. We're going to read this paragraph. We're going to change it from wordy to mathy. Right now, it's 2 full lines of words. We're going to change it to math symbols. Here I go. Oil spills, circular pattern. Okay, we've kind of already written that. The radius of the spill, it's a circular pattern. The radius of the spill increases at a rate of 1 meter per second. I want you to take that phrase and change it to math, like a math expression or a math equation. The radius has a rate of change of 1. Here's how you're going to write it. The rate of change of the radius. The rate of change of the radius with respect to time is 1. Let's keep going and see if it kind of comes together for you. How fast, find. How fast is the area changing? Oh, now it's talking about the rate at which the area is increasing. How fast, at what rate is the area increasing? So it's telling me to find dA dt how fast is the area increasing? Find dA dt at the moment when the actual radius, not the rate, but the actual radius is 30. I took pretty much this whole paragraph and put it into mathy terms. The rate of change of the radius is a constant. It's 1. Find how the area is changing when the radius is 30. So here's what I'm going to do. We've already got the problem set up over here. We wrote our area formula. We've got, this is how the area changes. This is how the radius is changing. All we have to do is just sub in those numbers. So hang on a second. I'm just going to copy this equation, but I'm going to color code it for you. So I'm bringing this down here. So dA dt is equal to 2 times pi times r times dr dt. Okay, I just copied this right here. And now my colors match what I've done in the problem. So dA dt, that's what we're supposed to find. Got the 2, I got the pi, r. We need to plug in 30 for r, and we're going to plug in 1 for dr dt. I actually wrote it wrong. I'm supposed to write it like this. But anyway, the ADT when R is 30 is going to be 60 pi. 60 pi, ooh, let's put units on that. Meters and seconds. Okay, so this represents how fast the area is changing per time. So your units, this is how the area is changing. Your units need to be area units per time. Area units per time. Area per time. This is how fast the area of the circle is growing when the radius hits 30. Now, to try to help you understand that just a little bit, I can show you dAdt when R is 2. I just plug 2 in and I get plug 2 in, I get 4 pi. Plug 4 in, I get 8 pi. Right? Plug 10 in, I get 20 pi. So think about this. When my radius is 2, think about how big the circle is. When my radius is 4, think about how big the circle is. Okay? Look at how much more area has been added on. Look at how much more area has been added on when the radius only increased by 2. What about when my radius is 10? When my radius is 10, look how much more area was added on, right? So you can see that R is growing at a constant rate. R is 1, R is 2, R is 3, R is 4, R is 5. That's constant. It's a constant rate. The area, however, when R is 2, this is how fast it's growing. When R is 4, oh my goodness, now the area is growing faster. When R is 10, holy moly, the area is growing faster. When R is 30, the area is growing even faster. Okay? So that's kind of the cool thing about related rates. One aspect of our shape can be growing at a constant rate, while another aspect of our shape is growing at a rate which is changing. And that's kind of cool. Okay, so when you're doing this homework tonight, you're going to focus on writing it, good notation, and we're going to go from mathy to wordy. Color-code it if you need to. Pick a color, underline it in the problem, write it down, mathy. Switch colors. Underline something else, write it down, mathy. Okay? Good luck.